Welcome to this memory management. Memory management provides a detailed description of various ways of organizing management memory hardware. The program must be brought into the memory and placed within a process for it to be run. If we want to execute any program, that should be brought into the main memory for execution. Then main memory registers are the only storage CPU can access directly. The memory unit only sees a stream of addresses and read request or addresses and data and write request. Register access in one CPU clock or less than that. Main memory can take many cycles that may cause stall or idle. The cache sits in between the main memory and CPU register to reduce the time taken to access data from main memory. The protection of memory required to ensure correct operation. Then base and limit registers. The pair of registers called base and limit registers define a logical address space. The CPU must check every memory access generated in user mode to be sure it is between base and limit for that user. For example, here this is the limit, here this is an base address. So the address of program may be between this base and limit. If it exceeds beyond the limit, then the address error will occur. This will be given by the operating system. Then hardware address protection. This is I said here if any CPU address is going to be generated, that should be greater than the base and should be less than that limit. Okay, in such case they can access data from the memory. Otherwise, the OS has to give the error, addressing error. Then address binding. The program on disk ready to be brought into memory for execution from an input queue. Without support must be loaded into the address 0000 starting address. The inconvenient to have first user process physical address always at 000. So further address represent different ways and different stages of program's life. Source code address usually symbolic. The compiled code address bind to the relocatable address. We cannot store the address program in the starting address. So this is going to be relocated. Anyway, the address will be calculated from the starting address 0. So whatever the exact location, this is going to be relocated. The linker or loader will bind the relocatable address to absolute address. So whatever address given in that object code, that is added with that relocatable address by the linker or loader. Each binding maps one address space to another. The binding of instruction data to memory. Address binding of instructions and data to memory address can happen at three stages: compile time, load time, and execution time. If memory location known in prior, the absolute code can be generated during the compile time and the recompile code start the relocation changes. Or load time, it must generate relocatable code. Okay, if starting address is with 0, the address is 40 means the relocatable code is 4000 means that should be 4040. Like that, this address need to be changed. Or runtime, the execution time. Binding delayed until the runtime if the process can be moved during its execution from one memory to segment to the another. It needs hardware support for address mapping using base and limit registers. Then multi-step processing of user program. Yes, initial source program will be given for compilation. The compiler generates the object code based on some address. It's called absolute address. Then what are the other modules need to be added? The library function that will be run by the linkage editor. Finally, we have a module for loading into the memory for execution. This will be done by the system software called loader. Then if you want to add any system libraries during runtime, that is added, program is executed here. So this is a time for compile time, loading time and execution time. The logical versus physical address space. The concept of logical address space that is bound to a separate physical address is central to proper memory management. The logical address generated by the CPU, also referred to virtual address. The physical address seen by the memory unit. The logical and physical address are same in the compile time and the load time addressing bind schemes. The logical and physical address are different in execution time address binding scheme. The logical address is set of all logical addresses generated by a program, and the physical address space is the set of all physical addresses generated by the program. Memory management unit, the hardware device that at runtime maps virtual to physical address. Many memory possible covered in the rest of this chapter. To start, consider simple scheme where the value in the relocation register is added to every address generated by a user process at the time it is sent to memory. Base register is now called relocation register because usually you'll add with the base value. Now its relocation register is having the starting address where it is going to be relocated. The user program deals with logical addresses. It never sees the real physical address. The execution time binding occurs when reference is made to location in memory. The logical address is bound to physical addresses. Then dynamic location using relocation register. The routine is loaded until it is called. See, this is CPU, logic address is 346, but if the starting address is 0 means then this will be 346. If starting address is 14,000, then what may be the exact address? So this will be added with this. So it will get 14,346. So buffer memory space utilization, unused routine is never loaded. All routines kept on disk in relocatable load format. They useful when large amounts of codes are needed to handle infrequently occurring cases. No special support from the operating system is required. It's implemented through program design. OS can help by providing libraries to implement dynamic loading. Dynamic linking. Static linking. System libraries and the program codes combined by the loader into the binary program image. The dynamic linking postponed till the execution. The small piece of code stub is used to locate the appropriate memory resident in library routine. Stub replaces itself with the address of the routine and executes the routine. So operating system checks if routine is in process, the memory address. If not, the address space add to the address space. Dynamic linking is partially useful for libraries and system also known as shared libraries. Then next concept is about swapping. The process can be swapped temporarily out of memory to backing the store and brought back into the memory for continued execution. When executing a program, for some purpose, some part of the program is need to be kept in the secondary device. Later, this will be loaded into that memory for continuing the execution. This is called swapping. Moving that program between the main memory and secondary memory is called swapping. So total physical memory space of process can exceed physical memory. Backing store fast disk large enough to accommodate copies of all memory images for all users. Must provide direct access to these memory images. What is rollout and roll-in? Swapping variant used for priority-based scheduling algorithms. The lower priority process swapped out so higher priority process can be loaded and executed. The major part of swap time is transfer time. Total transfer time is directly proportional to the amount of memory swapped. System maintains a ready queue for ready-to-run process which have memory image on disk. Does the swapped out process need to swap back in same physical address? Depends on the address binding method. Plus consider pending I/O to or from process memory space. The modified version of swapping are found on many systems like Unix, Linux and Windows. Swapping normally disabled. Started if more than a threshold amount of memory allocated. Then disabled once again. Memory demand reduced below threshold. So it's not taken frequently. So when required, we have more number of processes. We cannot hold in that. memory, that time we can place the some process. Only few will be taken out from the main memory and placed in the secondary memory. So here swapping is taking out of the process from the main memory and placed it in that secondary storage. Then it has to be bring back to that main memory. This is called swap out, placing that process from main memory into that secondary storage is called swap out, and placing that process into the main memory again back is called swap in. Then context switch time including swapping. If next process to be put on CPU is not in memory, need to swap out of your process and swap in target process. Context switching time can then be very high. 100 MB process swapping to hard disk with transfer rate of 500 MB per second. So swap out time of 2000 milliseconds plus swap in of same size process, total context switching swapping component time of 4000 ms, that is 4 seconds. So you can reduce if process size of memory swapped by knowing how much memory is really being used. Maybe using the system calls request memory and release memory. So context switching time and swapping. The other constraints as well on swapping. Pending IO can't swap out of IO would occur to wrong process. Always transfer IO to kernel space, then the IO device. No, it's also called double buffering. It's also added overhead. So standard swapping not used in modern operating system, but modified version is used. Then next about contiguous allocation. The main memory must support both OS and user processes. Limited resources must allocate efficiently. The continuous allocation is one yearly method. Main memory usually into two partitions. The resident operating system usually held in low memory with interrupt vector. User process then held in high memory. Each process containing single continuous section of memory. Continuous allocation. The contiguous allocation. The relocation registers used to protect user process from each other and from changing operating system code and data. Base register contains value of smallest physical address. The limit register contains range of logical addresses and each logical address must be less than the limit register. MMU can map logical addresses dynamically and can then allow actions such as kernel code being transient and kernel changing size. Hardware support of relocation of limit registers. Here the CPU is giving the logical address which compare with the limit register. If it is less than the limit register, yes, then we can give to that address for adding with relocation register and final physical address is calculated. If the given logical address is beyond the limit of beyond the limit register, then there is an addressing error. Then multiple partition allocation. Here multiple partition allocation, the degree of multiprogramming limited by number of partitions. The variable partition, that means size or efficiently given. Then whole, the block of available memory, the holes in the sense if you allocate in between you have some memory, this cannot be used by any other process. So holes varies of size are scattered throughout the memory. When a process arrives, it is allocated to the memory from hole large enough to accommodate it, but not continuous. The process exiting free partition, adjacent free partitions are combined. So this may be combined using allocated partition or free partition hole. The dynamic storage. Allocations, the first fit, best fit and worst fit. How to satisfy a request of size n from a list of free holes. The first fit, allocate the first hole that is big enough. So wherever you have a process, then you want to load which is available first, there we are going to fix it. Suppose the problem is the hole size is more, then the process says then most of the space will be wasted. The best fit. Allocate the smallest hole that is big enough. Search entire list. So you want to load that process, then you have to see which is closer to that. Okay, then see the entire list and find which is suitable for the particular, then you have to allocate. Then worst fit, allocate the largest whole for the smallest one. Here we'll get the large amount of space will be left over. So first fit, best fit better than worst fit in terms of speed and storage utilization. Then fragmentation. There are two types of fragmentation. The total memory space exists to satisfy the request but not continuous. So here what happened? Here we have a storage space. Okay, here these are all the storage space we have. Here also we have it is occupied by some process. Now we need some process. For example, this is 10 MB, 10 MB is free here, here 10 MB is free here. Okay, now we need a memory size of 20 MB. It's available but not continuous. This is called external fragmentation. Internal fragmentation, allocated memory may be slightly larger than the requested memory. Okay, here we need a process. This is the allocated memory for this process. Only it needs less amount of space but more amount is allocated, so the portion is wasted. This is called internal fragmentation. The size difference is memory internal to a partition but not being used. So first fit always analysis reveals that given n blocks allocated, 0.5 n blocks lost to the fragmentation. Then reduce of external fragmentation by compaction. Compaction means whatever is available, just move this, just compress this for making this available data at the end of the memory. Then the shuffle memory contents to place all free memory together in one large block. The compaction is possible only if relocatable is dynamic and is done at execution time. Then it's for IO problem. The latch job in memory while it is involved in IO. Do IO only in OS buffers. Now consider that backing store has same fragmentation problems. Yes. So the internal external fragmentation. So internal fragmentation, you are allocating the process. Here it requires less memory but allocated one is bigger one, so this portion is wasted. But in case of external fragmentation, we are having some memory space. For example, this is a free space of 10 MB, this is a free space of 10 MB. We need 20 MB means it is not continuous, so we cannot allocate. So we can move everything in one side. It's called compaction. Thank you.